Right, recording is rolling. It's Thursday, December 9th, and starting today, going to do this midterm review. So this will last a few days. So here's the structure of the midterm. It's going to be in two halves. The first half is going to be 50 multiple choice conceptual questions, and those will be drawn straight from this review page that I gave you guys a while back. There's 99 questions here, and I will pick 50 of those, and that will be half the midterm. The other 50 points are going to come from 10 multiple choice problem solving questions. So, and that'll be there will be one or two questions per section. There's like kinematic motion and forces and energy and momentum and rotational. So, sorry. So at least one question from each of those. Well, this midterm is open notes. So no cell phones, but calculators obviously fine. Any notes that you guys take that you want to bring is okay. There's also a packet on your desk that looks like this. Well, here, there's a few pages here. Now, I only have enough for a class copy, so guys, the packet that's on your desk, are you guys gonna take that or leave that on your desk? Yeah, just leave that on your desk. But if you wanted this at home, here's a couple places you could get this. There's a few papers here, right? There's AP equations, which let you guys have access to because they could be helpful. There's variables map, so variables, what it means, the units measured in, a few other notes. Right. And then there's this review page that has section by section, what are some reasons you might use this particular framework, say like conservation of energy, for example, some common equations, examples, graphs. I did give you guys these 3 pages on the very first day of school back in August, or these are also posted to Google Classroom, so you have access to those there. But I don't have so much printing budget, so just leave this packet on your desk, and then all my classes can use it throughout the day and for the next couple weeks. Okay, so yeah, this next few days, do midterm review. If you guys remember, tomorrow your chapter 8 questions are due. So a lot of you guys have already turned those in because we've gone over all those in class. And then Monday, your guys' rotational dynamics quizzes due. Looks like this. And some of you guys have turned this in too, because again, we've covered all the stuff on it. So turned early is fine. Question I always get is, how do you calculate midterm grades? So let's go over this. Now, the formulas here are true for all your classes. So all your classes, the midterm counts for 20% of your overall semester grade. Okay, so 40% from quarter 1, 40% from quarter 2, plus 20% midterm is equal to your overall grade. If you want to have a little bit simpler looking equation, you can say, well, everything from August through now is going to count for 80%. Of course, I'm also going to put in your very last quiz grade when you guys turn that in by Monday. Okay? So you have 80% of your class grades plus 20% of your midterm is equal to your overall grade. Okay, so what might be more relevant question is, well, if you have some target semester grade in mind, maybe like I want to get an A, that would be 90%, or I want to get at least a B, then 80%. And you know what you have right now, because you can just look on Focus and see that. What do you have to score on the midterm? And you can solve that just by going through some algebra steps. And this is what it turns out to be at the end. The score you need on the midterm is equal to 5 times what you want minus 4 times what you have. So for example, let's say you have a 77 in some class. You're like, that's really close to B. Hey, I wonder if I could get it at an 80 so I can get it to B. Really, maybe this number should be 79.5 because it rounds up. Right? So plug in this formula, and you'd have to get this score here so that you could do that. Okay? So that would work. This is true for all your classes. So there you go. General way to get that. Okay. Here's the midterm schedule, which is posted to Google Classroom. You guys have access to that. Your very first midterm is going to be next Thursday, and that'll be for your 7th period class, and then it goes 1 and 6, 2 and 5, and 3 and 4. Okay. To tell you guys that I do have jury duty next Thursday, so I won't be here on that particular day. Probably just leave directions with the sub to give you guys time to study, because you'll be deep in midterms then. All right, so let's go through these review questions. Now, these questions here exactly follow these 99 questions that you guys have on this review. Okay, so we'll go over the answers. They go section by section. we'll do is do some conceptual questions. Then at the end of each part, I'll go over some graphs and some other examples with you guys too. So when you look at the speedometer of a moving car, you can see that car's what? But yeah, instantaneous speed. How fast it's going right at that instant. The speedometer reveals pointing at some speed. A train travels 6 meters in the first second, 6 meters in the next second, 6 meters in the third second. So it looks like every single second is going 6 meters. So what is the speed of that train equal to? 6 meters per second. But that's not the question. The question is, what is the acceleration of the train? And what's the answer to that question? 0. Yeah, 0 meters per second squared. Because it's not changing what it's doing. Anytime you have constant velocity, you have 0 acceleration. Acceleration is rate change velocity. Car starts from rest and after 7 seconds has picked up to 42 meters per second. What is the acceleration? Can you guys see the speedometer needle going? The car speeding up. Okay, so it goes from 0 to 42 meters per second and it takes 7 seconds to get there. How many meters per second was it picking up every second? 6. Yeah. So it's called 6 meters per second squared. This was sort of an equation type question, so maybe I should jot down some equations here. There are these 3 kinematic formulas that we kept shopping for this section. There was x equals v naught t plus half a t squared, right? Distance equals speed times time. That'd be the whole story if there's no acceleration. Or x equals 1/2 a t squared if something starts from rest. Right? And then you have both going on, just tag them together, initial velocity and acceleration. You guys got the speed something, I should say the velocity something picks up to is equal to the initial velocity plus acceleration times time. And there's also this third one, vf squared equals v naught squared plus 2ax. Okay. Now, all those formulas are on those printed pages that you guys get access to, of course, during the midterm. Open notes, but write down anything you want to. Okay. And we were just using this middle formula right here. It says start from rest. That means initial velocity 0. This boils it down to this. Okay. Picked up to 42 meters per second. Took 7 seconds. It'd be picking up at a rate of 6 meters per second squared. There you go. As an object falls freely in a vacuum, is its velocity increasing? Yep. Is its acceleration increasing? Falls freely in a vacuum. At the surface of Earth, the acceleration would be equal to what? 10 meters per second squared? Oh, 9.8, but a lot of times around that to 10 meters per second squared. And does that change? No, that's just a constant value. So acceleration is not increasing. So velocity is increasing by 10 meters per second. You know, actually, let's do a quick graph for that. Let's do a velocity versus time graph for free fall. Say object falls from cliff. Right? Top of a cliff, drop something. Okay. Let's do velocity in meters per second versus time in seconds. Okay. Say it starts from rest. At time 0, it's moving 0 meters per second. And then let's call it down positive, if down is the positive direction. Okay. Can you guys draw that graph? You guys know what that graph looks like? Did you guys draw that right there? Right. And what's the slope of this equal to?
The acceleration.
Yeah, the acceleration, right? And if we're talking about free fall, that'd be free fall gravity, g, which might be like 10 meters per second squared if you're on Earth. Right? So at 1 second, it's picked up to 10 meters per second. After 2 seconds, it's up to 20 meters per second. So 10, 20, right? You just keep going. 3, 30, and Right? One slow up. Okay. 440, 550, rate will pick up. Now, this would be true in a vacuum. Okay? Now, after we did the linear stuff, we started bringing in forces. And if you introduce air drag, that actually changes this graph a bit. Can you guys draw what this graph looks like if you introduce air drag? This is one of your guys' quiz questions. Like in a vacuum, it looks like this. Okay? But if you introduce air drag, hey, do you think if you're falling long enough through air, you'll eventually reach terminal velocity? You guys remember that? Okay? That's like a state of equilibrium, right? Terminal velocity. Okay? So that the force down equals the force up. You just go down constant speed. And if that were true, this graph might look something like, well, we have to do something with a horizontal asymptote. It'd be something like V terminal. Right? That V terminal would depend on the shape of the thing that's falling through the air. Right? So it could be like if you have a parachute, I bet this horizontal asymptote would be lower. And if you don't have a parachute, it would be way higher on this graph. But something to do with that. And then this V versus T would start out like through vacuum, but it would eventually tend towards this horizontal asymptote like that, wouldn't it? Okay. And then you just go down constant speed. So this is no air drag, like through a vacuum, and this is with air drag, bridge terminal velocity. In the absence of air resistance, objects fall at constant acceleration. Suppose an object is in free fall. Each second the object falls, is it the same distance as the second before? No, because I remember this right here. Distance as a function of time. If it's in free fall, it's accelerating. Remember, distance is proportional to t squared. So every single second, it's picking up, it's falling further than the previous second. Okay? Like, you guys remember dropping a ball off a cliff after the first second? Here, let's run some numbers. Let's say you drop it. So this term goes to 0, starts from rest. Okay? Pop in 10 meters per second squared here. Let's say after 1 second. 1 squared times 10 divided by 2 is equal to what? Like 5 meters. Right after the first. Maybe I'll sketch this out. Let's do a table and a graph and the whole deal. Let's say you drop, fall off cliff. Right. Let's call it down the positive direction. And you guys got, of course, these formulas to work with. Now, if you drop it, then V naught would go to 0, so that simplifies it to what you can see over there. X is 1/2 AT squared. The speed it picks up to is just A times T. Okay. Let's do something like tables and graphs. Right. You guys remember these 3 graphs we made over and over back when we were doing kinematic motion? There was X versus T, V versus T, and A versus T. Right. I've got a table of values going out here. Let's see, there was time, acceleration, velocity, displacement. Okay. So time could go 0, 1, 2, 3, 4, 5, 6. It maybe takes 5 seconds for something to hit the bottom of the cliff. Okay. Acceleration. Now, as soon as you release it, it accelerates down at about 10 meters per second squared. And if there's no air drag, isn't that true all the way down? 10 meters per second squared all the way down? Okay. The speed it picks up to, well, if it starts from rest, when it started out at 0, okay, and then picks up to 10 meters per second, then 20, 30. We just did a graph a moment ago. Here, this graph right here. 1 second, 10, 2 seconds, 20 meters per second, 3 seconds, 30 meters per second. Okay. That's this column right here. Okay. But how about X? You guys remember how the falling distance is 1/2 GT squared? So if this A is G, right? Okay. So let's call the top of the cliff point 0, and everything below that will be in the positive direction. Okay. So 1 second. 1 squared times 10 over 2 is 5 meters. It'll fall 5 meters in the first second. Okay. How about after the second second? 2 seconds squared times 10 divided by 2. Is that 20 meters? After 3 seconds, 3 squared, that's 9, times half of 10, that's 45 meters. 4 squared, 16 times 5 is 80 meters. And then 5 squared times 10 divided by 2, it's about 125 meters. Oh, hey, because that's the college equation, isn't it? What's the falling distance as a function of time? You guys remember doing all that? Okay. What do these graphs look like? Okay. I usually start with this middle graph, V versus T, but we just did that. And it takes this shape, and the slope is G, or 10 meters per second squared if you're on Earth. Of course, if you go to a different planet, that number will change. But okay. How about acceleration versus time? What does that graph look like? You guys draw that graph? Did you guys just draw a horizontal line? Right? With so constant coordinate, and that coordinate would be g, or 10 meters per second squared if you're on Earth. Flat. Remember how the slope of v versus t tells you the coordinate of a versus t? How about x versus t? Now I'm going to define the top of the cliff as 0.0, so that at time 0 it's at 0.0. So I'm putting that point right there. Okay. Drop this ball, let it fall. Okay. Did you guys turn these into xy coordinates? Oh, tx, I should say. Okay, tx. So 1 second is falling 5 meters. That's times 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So 25, 50, 75, 100, 125 meters. So after 1 second, it's fallen 5 meters, 2 seconds, it's up to 20, 3 seconds, up to 45, 4 seconds, up to 80, and 5 seconds, 125 meters. Hey, what shape is that? Right there. What's that called? That is a parabola. Parabola, right? And the vertex is right at the origin point in this case. The vertex is at 0, 0. Okay. You guys remember all that? Ball tossed vertically upward rises, reaches the highest point, and then falls back down to its starting point. During this time, the acceleration of the ball is always what? Is which way does the weight point? Downward. And if you divide by mass, isn't the direction of the acceleration always downward? Okay. Now, the velocity is up when the ball is moving up, and the velocity is down when the ball is moving down. But the acceleration is always down. It's always tending towards down. That's the way it wants to go. Okay. Ball's thrown straight up. At the top of its path, its instantaneous speed is what? 0 meters per second at the very top. A ball is thrown straight up. At the top of its path, its acceleration is equal to what? How about 10 meters per second squared? Downward, right? Magnitude direction. Okay. Here, let's do, since we're talking about throwing balls straight up in the air, let's think about that. Okay. Let's say you go to the cliff edge, so at cliff edge, let's throw ball upward, and then later on we'll say throw ball downward. And let's define down is the positive direction. Okay. Let's do graphs for all these. X, V, and A versus T. X, V, A versus T. X, V, A versus T. Okay. This is still linear motion, right? You're going to the edge of the cliff and you're throwing something either straight upward or straight downward. Okay. Let's start with the upward. Right? So you take a ball, throw it straight upward. Now, if down is considered positive direction and you throw something upward, again, I'm going to start with the V versus T. I usually start with this one. Okay. Then at time 0, where should the intercept be? In the positive or the negative territory? If you throw it upward, which is the negative direction, shouldn't that land you like right here? Wouldn't that be V naught right there? Okay. So at time 0, ball's leaving your hand, moving in the negative direction. Okay. Also, if you throw the ball up, then right after it leaves your hand, is it speeding up or slowing down? Slowing down, right? Which is a hint that maybe its velocity is tending towards 0. Can you guys draw the rest of this graph? Did you guys draw that right there? The slope is g, 10 meters per second squared. And, oh, look at this. Right there, you guys have the velocity is 0 at that point? Because that would represent the point where it's like maxed out, right? Where it's at the highest point. How about A versus T? Did you guys just draw that right there? The coordinate G? This slope, this coordinate, same thing. How about X versus T? Well, if you throw something up, it's eventually going to come back down, so this one's going to change direction. Okay? Let's define the top of the cliff as 0, so we've got 0, 0 as an origin point, so it would have to define that. Okay? I do remember, based on this V versus T graph, it does max out its height right at this time. So there's something special going on at this time, right? Okay. And it looks like down is positive. I threw it into negative territory, throwing it upward. Is this going to take a parabola shape? Parabola? Yeah. With the vertex being right there. Say it takes like a second to reach the top. Take a second, come back down, and it's just going to continue on like a parabola shape, isn't it? Parabola. How about throwing the ball downward? So start with V versus T. Did you guys draw that right there? V versus T? Still has a slope of G. It's still accelerating at 10 meters per second squared downward. Okay. It just got a head start. Let's give it a boost. Okay. How about A versus T? Did you guys draw the exact same graph as before? Okay. These graphs are identical, aren't they? Okay. Once something's in free fall, it doesn't matter if you threw it up, threw it down. It's accelerating towards the ground at 10 meters per second squared. Okay. How about X versus T? So you throw it down, it's going to speed up down. It's always going down. Let's call it the top of cliff 0. Okay. Is this still going to be part of a parabola? Yeah. Actually, you know what? I remember when I threw the ball upwards, it had to come back down and then past the original start point, and then it continued on a slightly curved parabola. Hey, what if I just take this and copy paste that right over here? Isn't that what this is going to look like? Like a piece of a parabola? This is a parabola. Maybe not super obvious, but it is part of one. The vertex is not there. The vertex is like off the graph. It's not even on the graph. So throw a ball straight up at the top of its path. Its instantaneous speed is 0, but its acceleration would be 10 meters per second squared. A car accelerates at 2 meters per second squared. So you guys see the speedometer needle moving, it's picking up 2 meters per second every second. Assuming the car starts from rest, how much time would it take to pick up to 20 meters per second? What do you guys say? How about this? Right. Car starts from rest. That means this is number 0. Right. It's going up to 20 meters per second. And it's picking up 2 meters per second every second. So what's time equal to? 10. 2 times 10 is 20. Okay. Right. Speedometer needle picks up 2 meters per second. After 10 seconds, it's going 20 meters per second. And if a freely falling object were somehow equipped with a speedometer, or the way I phrase that usually is if you point a radar gun at it or a motion detector, its speed reading would increase each second by how much? 10 meters per second. Okay. As long as you're on Earth, ignore air drag. We're just talking about this right here. Picks up 10 meters per second every second. Okay, that's the stuff. A freely falling object starts from rest. After falling for 6 seconds, it will have picked up to a speed of about what? So starts from rest. This number is 0. This way. Picks up 10 meters per second, and it does that for 6 seconds. It's picked up to a speed of what? 60 meters per second. Exactly, 60. And you can sort of add that to this table here, couldn't you, too, right? Just add on another second to bring us up to 6 seconds. And then, oh, whoops, I made a typo here. This should have been 50. I was thinking. Okay. So the next one would have been here 6, this 10, 60 meters per second. And see, 6 squared is 36 times 10 is 360 divided by 2 is 180 total meters. If you had a 180 meter tall cliff, it would take 6 seconds to reach the bottom, and it would be moving at 60 meters per second at the bottom. It's crash speed. You guys good so far? Solve a couple of cliff type questions. Maybe you guys have got, let's see, some cliff. Let's say you release a ball from rest, and I want to know if you know the height of the cliff. Let's say this height is, hey, let's make it 125 meters. Can anybody tell me the final? What's the speed that ball is crash landing into the ground? What I might do is maybe make a checklist. Tax BV. Okay? So I could say, well, what numbers do I have? What do I want to know? Okay. Well, I know the height change, like the distance is moving, is going to be 125 meters. Okay? I did say if you drop it, release it from rest, that make V naught 0 meters per second. Okay? You guys take physics in college. A lot of times that's sort of hidden number because they don't expressly tell you V naught is 0 meters per second. For those who like release from rest, means that. I'm trying to figure out how fast is a crash landing. And I also know if you're on Earth, this would be 10 meters per second squared. Okay, so we've got these three variables. We're looking for this variable. Notice the one that I don't really care so much about is time. Oh, you could ask that, how much time, but let's think about that later. But to answer this really directly, which of these equations says nothing about time? First, second, or third? The third one. Yeah, I bet we could apply this third one and get the answer right away, right? Let's try that out. V final squared equals V initial squared plus 2AX. Solve for this. V final squared equals, okay, well, V naught, and V naught squared just goes away, 0. So we got 2 times 10 meters per second squared times that height at 125 meters. Square root both sides to undo the square. The final is, I know what the answer is going to be. It's going to be 50 meters per second. Now you guys can run your calculators and check me on that, but I know that's going to be the answer because we've already done that in class. You guys remember this table right here? Drop a ball off a cliff. After 5 seconds, it's fallen 125 meters, starting from rest. It's picked up to a speed of 50 meters per second. So that has to be the answer. That has to be how it play out. In fact, if you went back and solved for time, what's time equal to? 5 seconds, because it's consistent with that whole table. Also, those equations, pull up these 3 equations, solve for time. I guarantee you that they'll come out to 5 seconds. Let's try it. Maybe this one right here. Let's try this. So I said fell 125 meters times 2, divide by this A 10. You guys remember this whole piece is just 0, so whatever. Just ignore that. Okay. Then take the square root. Yep, it's 5. Time is 5 seconds. Guys good so far? All right. Oh, time up here. All right, and we're back. A ball is thrown to the air at some angle. At the very top of the ball's path, its velocity is entirely what? Solve this one with a picture. So, got ground, got this ball. I'm going to throw it into the air. That ball is like V naught, but be careful with that. Notice I didn't make it strictly vertical or horizontal. It's on some weird angle. So it's going to follow this path, right? Like a parabola shape. Okay? At the very top of its path, its velocity is entirely what? Vertical or horizontal? Guessing horizontal, right? It's only moving horizontally. Okay? Actually, that horizontal component of motion, isn't that true all the way throughout its path? Because the ball is accelerating, but only vertically. Okay? So here, if I go back to the very beginning and I split that initial velocity into components, you guys see this Vx? See how that's the same Vx? Okay? Just stays the same all the way through. Okay? Now, the Vy, I'm really going to call it V naught y. Okay? And then that's going to shrink to 0 by the top, gets to the top, and then become negative all the way back down. Okay? Could you guys solve for V sub x, the horizontal component, if you knew the throwing speed and also the throwing angle? Could you guys get that? Hey, is this a right triangle? You guys remember some trigonometry? What is V sub x based on this throwing speed V naught? It's V naught multiplied by what to do with this angle? Sine or cosine? Looks like Vx is adjacent to this angle, isn't it? Yeah, that's cosine. Okay, you guys remember that? Okay. So, for example, let's say you threw this thing at like 5 meters per second, and that angle is 37 degrees. Cosine of 37 degrees. How fast would it be going across the field? Well, that would be, say, 5 cosine 37 degrees. I'm looking at 4 meters per second. In fact, it's pretty much exactly 4 meters per second because that angle is a special angle. 37 degrees you always see in a 3, 4, 5 right triangle. If you have a hypotenuse that's a factor of 5, then the legs will each also be an integer value, just like that. Or I should say multiple of 5. A ball thrown in the air will never go as far as physics ideally would predict because, here's the deal. Let's say we solve this out to figure out like how far is this thing going to land, which we could. You'd say, well, take the vertical information, and that would constrain the time of its flight. And then if you know the time of its flight, you take this 4 meters per second that it's going across, or this V sub x, okay? Multiply it by that time, it would tell you how far it lands. Okay? Then we all go outside and we start throwing balls, and they're always going to consistently land a little bit short. Why? What factor do we famously ignore in this class for a long time? Air drag, air drag. Yeah, the fact that air friction acts on the ball is going to make it land a little bit short. Airplane flying into a headwind loses ground speed. Airplane flying with the wind gains ground speed. But what if the airplane flies at right angles? What if the crosswind is at right angles to the motion of the plane, to the direction of the plane? Does the plane go faster or slower relative to the ground? Okay. You guys remember this plane? Throwing a velocity vector here. Let's say that its engines relative to the surrounding air can power it forward at 80 kilometers per hour. 80 kilometers per hour. It's going straight north. Okay? And that's all fine and good until it runs into this crosswind. Let's say it's a pretty good crosswind. It's blowing straight east at 60 kilometers per hour. Okay. Now the first part of that setup said if the wind is blowing with the plane, obviously it's going to be moving really fast relative to the ground. You can watch the shadows of maybe 100 kilometers an hour. Okay? If it's fighting the wind, it's going to be going really slow relative to the ground. Maybe it's kind of 50 kilometers per hour. Okay? But what about this crosswind that's not pushing it forward, but also it's not really fighting it either? How fast would its shadow be moving across the ground? Okay? Did you guys solve for that? Notice I added these vectors together tip to tail. Okay, plane's always trying to go north, the wind's always blowing east, tip to tail. Wouldn't there be a resultant vector from the tail of the first one to the tip of the last one? And if you have many vectors, you can add them all tip to tail like this. I've just got 2 vectors here. Okay. This is the resultant vector. Okay. And wouldn't the magnitude of this resultant represent the ground speed of the plane, like how fast its shadow is moving across the ground? Okay. Who can tell me what the answer to that is? What's the magnitude of that resulted? Yep.
100 kilometers per hour.
It is 100 kilometers an hour. How'd you know that?
It's a 3, 4, 5 right triangle.
Exactly. That is a 3, 4, 5. Yeah. Scale it by a factor of 20. Right? That's it. So this is Pythagorean theorem, square root of 60 kilometers per hour squared plus 80 kilometers per hour squared. Square root of that whole thing gives Pythagorean theorem. That is 100 kilometers per hour. Yeah. And using the 3, 4, 5 geometry, we'll get it to you real fast. Just scale it by a factor of 20. That's how fast the plane shadows move across the ground. There's another question I could ask, which is the plane, even though the plane is pointing straight north, it doesn't actually move straight north anymore. It's kind of northeastish. Could you guys quantify what this angle theta is? Who remembers how to do that? Theta. Need some kind of inverse trig, right? Let's say you played off inverse tan. That's usually a classic one I like to draw. Inverse tan of, see, tangent had something to do with which two sides of the triangle. SOHCAHTOA. Exactly, opposite adjacent. So tangent of theta is opposite over adjacent. So inverse tan of opposite over adjacent is the angle. Okay, guys remember tangent of an angle is equal to a ratio. Inverse tan of a ratio is equal to an angle. Okay. Kilometers per hour, those cancel. You should get 37 degrees. I bet you got 37 degrees. Okay. Inverse tan, 60 on 80, 37 degrees. There you go. When in orbit, a satellite such as the space shuttle is, I'll tell you what they're looking for here, it's just simply a projectile. The idea is, this was the only question in this group of questions from this set of materials that involved projectiles considering a curved Earth. Okay. All the other projectile questions were assuming like a flat surface. Okay. But yeah, if you're going fast enough, you might actually consider the curvature of the planet that you're going around. So yeah, anything that's in orbit around the Earth is a projectile that just is falling so that the it's like falling around the curve of the planet. So it's not actually getting any closer to the ground. All right, there's actually that's all their projectile questions. I have one more projectile question for you guys though. Suppose you guys remember this. Thank you. You guys remember how'd you do that lab where you took those spring launchers? And we'll say the question is, what's the blast speed of this thing? So let's do a velocity vector. I'll call it v blast. Okay. What's the blast speed? Okay. And one way to get this was if you aim it straight horizontal, aim the blaster straight horizontal, it's supposed to be straight horizontal. Okay. And you happen to know the height of this cliff. Now, the ledge out there was about 4.5 meters. We got to round that to about 5 meters. Let's say height is equal to 5 meters. Okay. And then if you spot where the ball lands, it falls a nice parabola there, okay, and you know where it lands. So I'll call this x of, say 11 meters. Okay. And one more thing you have to know to be able to figure out the blast speed, and that's the gravity field that you're in. So I'll call this maybe 10 meters per second squared. Right? That right there is enough information to solve for the blast speed of that launcher. You guys did this. This was one of your early labs. Okay? Side note here, why would the gravity field be important? Because say if you took this to a different planet, or let's say you take this to the moon, where gravity is very, very weak. Okay? You could have the same blast speed and even the same cliff height, and when this ball land like way the heck off to the right and a really weak gravity field. So that's why that variable would be also be important. One of the things that I hope you guys get out of this class is to consider like what variables would be important or be able to play around with variables. Like, what if I increase or decrease this? How would that affect the situation? Okay. Right, so how do you get V-blast? Okay. When we were doing projectiles, one framework that I gave you guys was tax VV tables, but there was a separate one for horizontal versus vertical information, because those are directions that are independent of each other. And then say, well, the only thing that would have tied those together was how much time, right? The amount of time it takes to get from here to here is the same horizontally or vertically. Okay? So if you couldn't solve something in one direction, then you could get information, extract information from the other direction for it. Okay? So if that was helpful, awesome. If that was kind of confusing, then here, we'll just go through this either way. Okay? So try to get blast speed. Wouldn't blast speed, we'll start down at the bottom here, blast speed just be how far x it goes and how much time it takes to get there, x over t. And we know what x is. It's 11 meters. So 11 meters. And then, if only you knew how much time. Well, maybe you brought a stopwatch with you, so you timed it and got it that way. But that's maybe not the most accurate way to do it because it's really hard. I mean, this is a very tiny time interval. It's hard to get it exactly where it blasts and exactly where it lands, okay, with the stopwatch. There's a more accurate way to get the time, and that's to calculate it based on this drop height. Okay? Because isn't it true? Whether you drop something or blast it to the side, it takes the same time to reach the ground. Okay? So we're gonna have to go to vertical information, and that height is, I'm gonna say this, 1/2 gt squared. Okay? Now this is part of a bigger formula, right? V naught t plus 1/2 gt squared. Why did I leave off the V naught t part? Because when this ball leaves this launcher, how fast is it moving strictly up and down? It isn't. It's only moving to the side. Right? So its vertical component of velocity leaving the launcher would be 0. Right? If you just focus on the vertical stuff. Right? So V naught in the y direction goes to 0 and just boils down to this. Okay, so this drop height and this fall time, you say like one is a function of the other. So say you have 5 meters drop height and a gravity field of 10 meters per second squared. Can you guys tell me what the fall time would be? You guys think in 1 second? Actually, you guys have seen that earlier today already. You guys saw it right here. You drop the ball from edge of the cliff. After 1 second, it falls 5 meters. You guys remember that? Using this right here. So now we do have the time. Take this, pop it in right there, 1 second. Okay, so now it was going across the field, these 11 meters, in 1 second. That tells you 11 meters per second. That's the blast speed of that cannon. Just like that. Yeah, there's the whole thing right there. Blast speed. Yes, sir? After a cannonball is fired into frictionless space, the amount of force needed to keep it going equals how much? 0. That's Newton's first law of motion. That's law of inertia. Okay, so we're moving on to forces and Newton's laws now. Okay. The only reason anything would ever speed up or slow down is if there's a what acting on it? A force. Yeah, so like Voyager spacecraft, it's just going. There's no force. There's no reason for it to slow down. It has inertia. It just keeps going. If the force of gravity suddenly stopped acting on the planets, they would. Here, I'm going to draw you guys a picture and narrow it down to a couple of options. You guys tell me what's true. So you have a sun here, have some planet moving in, and say an elliptical orbit that's pretty approximately circular. But you guys know from Kepler it's actually elliptical. So have a planet parked right here. Well, not parked. It's in motion, right? So there's the planet going, going around. Does it have an instantaneous velocity in this direction right here? Okay? Like at that moment, it's moving that way. But the sun is pulling at right angles to that. Well, approximately. If it moves in a circle, it would be a perfect right angle. Okay? It's pulling, say, this way. So if there's a gravity force acting as a centripetal force. What would happen if you turned off gravity right at this point? Just boom, turn off gravity. Which way does this planet go? Does it continue tangent to that path? When I say tangent, see how I'm holding the roller like flush to this curve? It just touches it at one point, like flush to the curve. Okay. That's how I get that tangent line, that velocity. Okay. Or does the planet make a random 90-degree turn and then fly straight away from the sun? Which one of those is true? I bet the planet's gonna follow this path right here. Can't keep going tangent to its path. Okay. That's also a law of inertia, isn't it? A sheet of paper can be withdrawn from under a container of milk without toppling it if the paper is jerked quickly. Why? Is it because the milk carton has a lot of weight or a lot of inertia? A lot of inertia, a lot of mass, a lot of inertia. Yeah. Now weight would press down and maybe like increase the frictional force, which would not be very helpful. But yeah, a lot of inertia, tendency to like sit right there. That's mass, inertia. Guys, remember Paul Hewitt with the tablecloth trick? So all those Paul Hewitt demos, they're in a zip folder somewhere on Google Classroom from back in the day. Just want to go watch Paul Hewitt, might be a good review. The force required to maintain an object at constant speed in free space is equal to, zero. We just talked about that one 2 questions ago. Sort of a repeat question. That's the law of inertia. Equilibrium occurs when, let's see, all the forces acting on an object are balanced. That sounds good. The sum of the positive x direction forces and negative x direction forces cancel out? Yep. The net force on the object is 0? Yep. The sum of the forces up equals the sum of the forces down? Yep. Those are all looking like pretty good statements. Recently, just in the last few weeks, we actually added one more condition, which is what? For equilibrium, not only did the forces in each direction have to sum to 0, but also the what has to sum to 0? The torque. Yeah, that's a recent addition to that. Girl whose weight is 500 newtons hangs at the middle of a bar supported by 2 vertical strands of rope. What's the tension in each strand? So vertical bar, rope. Have this girl hanging at the middle. She weighs 500 newtons. What's the tension in each strand of rope? 250 newtons. Okay. Get that back in the day. I mean, just be half and half. You do know that the 2 ropes have to add up to the 500 to keep her in balance. Now, recently, you guys learned that if she's saying at any point how to figure out what each tension is, they have to add up to 500 though. But you have to use torque to figure out if she's hanging in other places. All right, I'll see you guys tomorrow.